Okay, this is going to be module 16 in physics, which deals with magnetism. The good news about this module is that we don't have to do any math. We will talk about we'll talk about some equations as they relate to a law that affects magnetism, but we will not be doing any calculations. So I'm sure you know some things about magnets, and you probably know that a magnet consists of a north pole and a south pole. And you probably also know that like poles repel and opposite poles attract each other in the same way that we saw with charges. Opposites attract and like poles repel. The other thing that is true of magnets, as far as we know, is that magnets always exist as a dipole. So they always have a north pole and a south pole. So if we were to take a magnet, so if we have this magnet and this is the north pole and this is the south pole, if we were to divide this magnet into two, what would happen is that each of those halves of the magnet would still have a north and south pole. So magnets always exist as a dipole. Now there is the possibility that there is a magnetic monopole, and scientists are certainly looking for it, but there has never been found a magnet that exists as a dipole. Okay, so just like when we studied electric charges, remember that charges create an electric field, while magnets create a magnetic field. And the strength of first of all, the strength of the magnetic field is inversely proportional to the square of the distance between the poles. So if you double the distance between the poles, then, so if you double the distance, then that means that you are going to decrease the strength of the magnetic field by a factor of 4. Okay, so it's inversely proportional to the square of the distance between the poles. If you decrease the distance, so if you decrease the distance by a factor of 2, then you are going to increase the strength by a factor of 4. Okay, so the strength of the magnetic field is inversely proportional to the square of the distance between the poles. And that's the same thing that we saw when we were looking at charged particles. So I think it was equation 13.1. I can try to put that up for you. So you remember this equation, F is equal to K times Q1, Q2 divided by R squared. Okay, so it's in the same way that the electrostatic force is inversely proportional to the square of the distance between the charges, the magnetic force is inversely proportional to the square of the distance between the poles. And just like electric charges, with electric charges you can draw electric field lines. Well, we can also draw magnetic field lines. And here's some of the characteristics. We'll do some examples, but the magnetic field lines come out of the north and into the south. Magnetic field lines never cross. And lastly, what we are looking at when we draw magnetic field lines is we are saying if the north pole of a magnet is placed into the field, what will be the directions of the magnetic field lines? So, the direction of the lines tell you the direction that the North Pole will point if it's placed in the field. Tell you the direction that the North Pole of a magnet will point when it's placed into that field. Now it's assuming that the North Pole of this magnet is free to move. So if you place the North Pole of a magnet into a magnetic field, the lines will show you the direction that the North Pole of that magnet will move. So, and then also the density of the lines will tell you the strength of the magnetic field. So the more lines that come out indicate that there is a greater strength in the magnetic field. Okay, so let's go ahead and look at magnetic field lines. So if we have a bar magnet that looks like this with a north pole and a south pole, then we said that they always come out of the north and go into the south, and they never cross. So the magnetic field lines will come out of the north and go into the south, out of the North Pole and into the south, out of the north and into the south, out of the north and into the south, out of the north into the south, out of the north and into the south. And we can also, we don't have to show all of them going all the way over, but these that are coming out of the north will go into the south. So we can show those coming into the south, and we can show these also coming into the south. Okay, so out of the north, every line coming out of the north will end at the south pole. Okay, so let's look at a little more a situation that's a little more complicated than that, but not too much so. So what if you have two magnets? This is north, this is south, this is south, this is north. So what would the magnetic field lines look for this situation? Okay, well, first of all, we can go like this. All of anything coming out of the north is going to go into the south. Anything out of the north is going to go into the south. And we would have the opposite, north coming into the south, north coming into the south. And then, you know, we can draw these lines. So within a magnet, you would have this, north coming into the south, north coming into the south, north coming into the south. But then you would also have lines that anything that would come out of the north here is going to go into the south here, out of the north into the south, out of the north into the south. Okay, so and there, you know, again, the number of lines indicate the strength of a magnetic field. Okay, so that's one example of how you could draw the magnetic field lines. If we look at on your own 16.1, there we see a horseshoe magnet. And here is the North Pole, and here is the South Pole. So what kind of, go ahead and take a minute and see if you can think about how the magnetic field lines would be drawn there. Well, the north is going to go into the south, north into the south, north into the south. And then we could have lines like this. And then we could also, you know, have these coming all the way around. You don't need to draw them showing that they come all the way around. You could just draw like this, coming out, and then this going back in. But and you could have those, that one coming out like that and coming in like that. So again, the magnetic field lines out of the north and they go to the nearest south pole, and again, the magnetic field lines tell us if we place the north pole of the magnet within the magnetic field, which way will that north pole point if it is free to move? Okay, so the next thing we need to talk about is what is it that creates a magnetic field? And we're going to do, when we get together next week, we will do an experiment that will use a battery and a compass and a wire, and we will get we'll get to demonstrate this a little bit next week. So if it doesn't fully, if you don't fully understand it, I hope you will understand it a little bit better after we've done an experiment next week. So when we were looking at current, well, what caused the electrical current? Well, the answer to that was that electrical current is caused by the flow of electrons. So as we were drawing electrical currents, we were looking at, what we were really looking at was the flow of electrons in a wire. Well, in a magnet, so remember that everything is made of atoms, and in the nucleus of an atom we have protons, which are positively charged, and we have neutrons, which don't carry a charge, and then orbiting around that nucleus in different shells we have electrons, and those electrons are negatively charged. So in a magnet, the charged particles that are flowing are the electrons that are orbiting around the nucleus. So moving electrons are just like moving charged particles, and so they are the thing that causes a magnet to be magnetic, is these movement of the electrons orbiting the nucleus of the atom. So then the question that you might be asking then is, since all atoms are made up of electrons, then why aren't all materials magnetic? Because every electron that is orbiting around a nucleus is creating its own magnetic field. Then why aren't all materials magnetic? And we know from experience that that everything is not magnetic. Well, that depends on whether they are magnetic or not. Depends on how many electrons there are and how those electrons are arranged, and whether or not they can cancel out each other's magnetic fields. So many atoms, there are many atoms that have an electron configuration so that the magnetic fields cancel each other out. So if the magnetic fields cancel each other out, then there's no net magnetic field. However, those substances can still react to a magnetic field. The electrons will move and they will produce a weak magnetic field that is opposite to the field that they were exposed to. there are a couple terms that we use to describe substances and whether they are magnetic or not. So the first term is diamagnetic. So diamagnetic refers to a substance that is made up of atoms with no net magnetic field. So this would be a situation that I mentioned previously where the electrons are configured in such a way that the magnetic fields created by individual electrons cancel each other out. Now, I did say that even though they don't have a net magnetic field, if they are exposed to a magnetic field, then the electrons will start to move, and that substance can produce a weak magnetic field, but this only happens when the atoms do not have a net magnetic field. And we'll see that that is not true in other cases. So diamagnetic substances that are made up of atoms that have no net magnetic field. Okay. Then, two other terms are paramagnetic and a paramagnetic substance is one in which they can become magnetic if they are placed in an external magnetic field. Okay, they can become magnetic if placed in a magnetic field. However, a paramagnetic substance will return to being non-magnetic if the magnetic field is removed. So they can become magnetic, but when you remove the magnetic field, then they return to a situation in which they are no longer magnetic. Okay, then the last one is called ferromagnetic. And ferromagnetic is where the magnetic atoms are aligned so that their magnetic fields add to one another. So in a ferromagnetic substance, we can have, if you want to look at figure 16.4, you will see that in the situation on the left, the magnetic fields are oriented randomly so that they basically cancel each other out. So that substance would not hold a charge. But on the situation in the right, you can see that the magnetic fields are all aligned in the same direction. So they will add together and they will tend to stay aligned for a long period of time, even if you remove the magnetic field in which they are placed. So if we can, so many atoms have an electromagnetic configuration that they will cancel each other out. Others do not. So we call them domains, but if the domains are arranged like this, and we have one going this way, okay, so these domains will cancel each other out and there will be no net magnetic field. So in other words, the magnetic fields will cancel each other out, and this is not will not be a magnet. But if when the substance, and we call these domains, if when the substance is placed in a magnetic field, if the domains all align with that field, so if they all align in this way, then they will stay this way for a long time, and sometimes even once the magnetic field is removed. So if this creates a really strong magnetic field, then that is what we consider a permanent magnet. So we could summarize it all by saying that electrons orbit around the nucleus of an atom, and that produces a magnetic field. In some atoms, the electrons are arranged so that the magnetic fields cancel each other out, and those would be called diamagnetic substances. However, if the electrons do not cancel each other out, then we say that that atom is magnetic. And an atom that is magnetic can either be paramagnetic or it can be ferromagnetic. If the atoms are misaligned so that their magnetic fields cancel each other out, then they're paramagnetic. But if the atoms align in little clusters so that they behave like a magnet, then it's ferromagnetic. If a ferromagnetic substance is placed in an in a external magnetic field that is strong enough, then the ferromagnetic substance's domains will stay aligned even after the external field is removed. And that is actually how we produce a permanent magnet. So it's made out of a rigid substance so that it can't remold itself, and it's placed in a very strong magnetic field so that when the magnetic field is removed, the magnetic domains stay aligned, and that substance would be considered a magnet. So one of the things that we will do next week that will help this make a little more sense to you is we will take some nails and we will run a current through those nails, and we will see if we can make them become magnetic. So again, a lot of this will make more sense after we have done some experiments next week. Okay, the next thing we're going to talk about is Earth's magnetic field. So you probably are aware that Earth has its own magnetic field. And a compass is a magnet because it's free to move and it always points north. There is a figure in your book, figure 16.5, that will show you the axis of rotation of Earth. And one of the things that you'll notice is that magnetic north is actually a little to the left of geographic north. So the compass points a little to the left of true geographic north. And the other thing that might be a little bit confusing is that magnetic north is actually the south pole of the magnetic field. So remember that we define the magnetic field as what will happen, what way will the North Pole point when it is placed into the magnetic field. So if we place the North Pole of a magnet, it's going to be attracted to the South Pole of Earth's magnetic fields. And the South Pole of Earth's magnetic field is actually magnetic north. So that can be a little bit confusing, but just think about what the definition of magnetic field lines are. Okay, so what causes Earth's magnetic field? Well, we know that Earth has a solid core, but then the outer core is actually comprised of molten metals like iron and nickel. And so that molten outer core has many charged particles in it, and those charged particles are swirling around. And as those charged particles are swirling around, that causes a current, and that current is what creates Earth's magnetic field. Your book discusses some of the theories related to why Earth's magnetic field tends to be decreasing. We don't have time to go into that, but there are two theories. One is called the dynamo theory, and the other is called the rapid decay theory. And the author of the textbook takes one view. Other scientists take another view. If you're interested in that, you can read that more carefully. So if we have a current, if we have a wire that is carrying current, and we just said that a wire that is carrying current will create a magnetic field. How can we tell the direction of that magnetic field? So when current flows through a conductor, a magnetic field is generated. And when current passes through a wire that is surrounded by a compass, the magnetic field that is generated by the current is stronger near the compass than Earth's magnetic field. So the compass needle will spin. The magnetic field is a circle and the wire is at the center of the circle. So we can predict the direction of the magnetic field from a wire that is carrying current. So if we have a wire and this wire is carrying a current, we use what is called the right-hand rule. So one thing that we know is that the direction of the magnetic field in a wire is circular. It's going to travel in a circle. So what we do with the right-hand rule is you place your finger in the place your thumb. You point your thumb in the direction of the current. So if the current is moving this way, we would take our thumb and we would place our thumb up in the direction of, and you guys know I'm a terrible drawer, but we would place our thumb pointing up in the direction of the wire, and then whichever way the fingers curl around, that will tell you the direction of the magnetic field lines. So if you take your thumb and point your thumb straight up, if the current is straight up, then your fingers curl around in a counterclockwise direction. So that would be the direction that the magnetic field lines would be. Okay, so let's look at a couple examples of this. So if we have a wire that looks like this, and if we'll call current is I, so if the current is going in that direction, then if you point your thumb in that direction, point your thumb in the direction of the arrow, then your fingers are going to curl down in this direction so that the direction of the magnetic field would be like that. Okay, so if these are your fingers, your fingers are curling in this direction. Okay, and then if we have an electric wire with current flowing through it, and now if the current is, so current is I, if the current is flowing in that direction, so if you point your thumb in the direction of the arrow, now which way are your fingers? We can use these to indicate the fingers. Okay, so now if I point that way, now the direction that the current will be flowing will be in this direction. So it's going to be going down like this, but then up like this. So down, down, up, down, up here, up here. Okay, so you can see that if you point your thumb toward the arrow, then your fingers are going to be curving down, and that's what we're trying to show in this figure. Okay, so that is the right hand rule, where you can tell the direction of the magnetic field lines if you point your thumb in the direction of the current. And you need to use your right hand in order for that to work. There are some people that, there is a way that you can do it using your left hand, but most commonly we use the right hand, so we will just use the right hand in this class. Okay, the next thing that we will talk about is called Faraday's law of electromagnetic induction. So Michael Faraday, who was a famous physicist, he was able to show that not only can, when charges move through a magnetic, when charges move through a wire, they can produce a magnetic field, but also that when a magnetic field moves, it can also produce charges moving through a wire. So if you want to look at figure 16.8 in the textbook, this is a simple experiment in which an ammeter is one that measures current, measures amps, in this experiment, there is a conductor that's arranged in a loop, and then a magnet is either pushed toward the loop or pulled away from the loop. And what you should notice, if you look at the figure on the left, that shows that when the magnet is pushed toward the loop, the amp meter measures a current in one direction. And then when the magnet is pulled away from the loop, the amp meter measures a current in the other direction. So it doesn't matter whether you move the magnet or the loop of conductor, as long as you make that movement away toward or away from the amp meter, you will measure a current. So Faraday developed what he called an electromotive force. And your book points out that maybe the word force is not the best term to use, because it's not really a force, it's a potential difference. But the electromotive force is called EMF. and that it's basically the potential difference between two sides of a battery when there's no current flowing. So in his study of this, Faraday was able to show that the amount of current that is generated is affected by different things. It can be affected by the strength of the magnetic field. It can be affected by the area of the loop. So if you look at that figure on figure 16.5, you can see the loop that is made out of the conductor. And it's affected by the angle between the magnetic field and the angle between the magnetic field and the area that is enclosed by the conductor. So the area between the magnetic field and the area of the conductor. Now I'm not going, I just want to show you you won't be asked to use this formula, but I'm going to show it to you and point out how each of these are affected. So So this stands for what is called magnetic flux. The B stands for the strength of the magnetic field. And A stands for the area that is enclosed in the loop. So this is the area of the loop. And then obviously the angle is the angle that's between the direction of the magnetic field and the vector that would be perpendicular to the area enclosed by the loop. So I'm not going to ask you to use this equation, but basically what you need to understand is that when the strength of the magnetic field increases, so if you increase the strength of the magnetic field, or if you increase the area, that is going to increase the magnetic flux. And if you consider a vector that's perpendicular to the area enclosed by the loop, you're going to get the maximum flux when that vector and the magnetic field are parallel. So the cosine of 90 degrees is 0. So that tells you that the magnetic field is perpendicular to that. When the angle is 0, the cosine of 90 is 0. So if the angle is 0, then the cosine of 90 is 0. So the magnetic field would also be 0. But the bottom line is that if you increase the strength of the magnetic field, or if you increase the area of the loop, that is going to increase the magnetic flux. So Faraday's law states that the electromagnetic force is equal to the change in the magnetic flux divided by the change in time. So what this means is that if you want to create a potential difference from one end of a loop of a wire to another, you have to change the magnetic flux that flows through that loop. And the faster you do that, the greater the potential difference, and therefore the greater the flow of current. So if we look back at that experiment, you can see that the A stays constant, right? So let me go ahead and write up this again. So we said that the magnetic flux is equal to B times A, and then times the cosine of the angle. Okay, and then all this is just the change in this and this. So this is just a change in this. So what this shows us is that, so the A is, in that experiment, the A is constant. The area of the loop doesn't change. And the angle also does not change. So those are not going to affect it. However, as the magnet is pushed toward the loop, that's going to change the strength of the magnetic field. Okay, so the strength of the magnetic field is going to change as you move that magnet toward the loop, because the magnet's getting closer to the loop. So then the magnetic flux changes. So if you change the magnetic flux, that is going to change the electromotive force that will cause current to flow. So then what happens when you pull the magnet away, which is what was illustrated on the right-hand side of that figure? Again, A is not going to change, and the angle is not going to change. But now when you pull that away, the electromagnetic force is going to decrease. So the magnetic flux changes, and if you change that electric magnet, that's still going to cause current to flow because you create an electromotive force. So the sign of the change, so when magnetic flux increases, the change in flux is positive. When the magnet is pulled away, the flux decreases, so the change in the flux is negative. So current flows in one direction when the magnet is pushed toward the loop. It flows in the other direction when the magnet is pulled away from the loop. So the direction of the current flow changes depending on the change in the magnetic force. Now, how does this apply to the ways that we create power today? So in electrical power plants today, with the exception of nuclear power, and I know nuclear power is being used more and more, but with the exception of nuclear power, in electrical power plants, magnets are spun inside large coils of wire. And as they spin, the angle changes. And as the angle changes, that's going to produce an electromotive force. Okay, so again, if we look back at this, the change in you get electromagnetic flux by changing any of these variables. So if we change the angle, that's going to change this, and then that will create an electromotive force, which can generate current. So if you get a change in this, and the faster that change occurs, the greater will be the electromotive force. So as the magnetic field changes, that produces this potential difference. So how are the magnets made to spin? Well, it really depends on the type of energy that is used. So in hydroelectric power, the magnets are hooked to a water wheel, and so as the current flows from the water, it turns the wheel, and that turns the magnets. So magnets are hooked to a water wheel. So the current from the water turns the wheel, and that in turn turns the magnets. If we look at things like coal or gas or wood, in these cases, the water, all of these are used to boil water. And then there is a turbine or a fan placed above the water. So the boiling water turns the turbine. So when the steam hits the blades, they turn, and then that turbine is hooked to the magnets. So as the magnets turn, then again, you're changing the angle between the magnetic field, and that causes it to create an electromotive force, which is a potential difference. So you're creating electric current because of that. Okay, I think we will stop there for today. We may talk next time a little bit about alternating and direct current, but we'll stop there for